Hi guys, welcome on the channel. So in this lecture we are going to talk about the electromagnetic inductions formula revision and the concept revision. So like there are the other similar videos available on this channel where I have just revised the formula for a quick revision where you can just have a recap of the complete chapter. You can get the idea of the complete chapter and the formulas. So once you have already studied, then you can just watch this video before solving your problems, so that you'll have the complete idea of the chapter, and then you can proceed to the questions like the J mains level questions, and then again you can just watch this video again, and then you can solve the J advanced question. Of course, like if we want to solve the question, then it should be a gradual step by step process. Like we will be solving very easy or single formula type of questions first, so that we can understand the application of the formula. And I think you must have done that kind of practice during your initial phase when you are going through the chapter. Now this video is meant for once you have already covered that and you have done some kind of practice, and now you are just doing the revision for your JEE mains, so that you want to do more questions. So that's why this video is here, so you can just go through this video. So yeah, before this lecture we cover before this chapter we cover the other chapters like the magnetic effects of the current, and maybe sometimes we also cover the magnetic properties of the materials. So where there we get the idea that the changing electric field creates the magnetic field, okay, whether it is Biot-Savart's law, and with the help of that we get that magnetic field due to a current carrying wire, then magnetic field due to a loop. All those things we have done in the previous chapter. Now think about it, that in the nature there is a symmetry. It means like the changing electric field can create the changing, or it can create the magnetic field. Then the variable magnetic field or something associated with that must create the reverse of that, which is the electric field. Yes, so there should be something like this, and the Faraday's law gives that itself. To understand the Faraday's law, you must understand first one thing which is called as magnetic flux. Now what is magnetic flux? Magnetic flux is similar to the electrical flux, where we say that the number of electrical field lines which pass through a area, that is the electrical flux, and that quantity we define with E vector dot A vector, or if E is variable, then we say that the electrical flux is integration of E vector dot ds vector. But here in case of the magnetic field, something like that only, the magnetic field lines which are passing through a area, and we say that the magnetic flux becomes B vector dot A vector. Here I have given this formula, and if in case the magnetic field is variable, then you will say integration of B vector dot ds vector, and the SI unit is Webers, or otherwise for the magnetic field we have the Tesla, so that's why Tesla meter square. Okay, now coming to the Faraday's law. What does Faraday's law says? So it says that the electric field or the electromotive force which will be created in a loop will only be created if there is a changing flux. It means if the flux is changing with the time. The instant when you stop changing this flux, that instant the electromotive force also that will become zero. Okay, so the relation is E equals to minus of d phi by dt, right? Here you can just remove this negative sign, and then you can say that E is equals to d phi by dt. It gives you the magnitude. Okay, now what is the significance of this negative? The negative will give us the direction. Now for the direction we have the another law which is based on the conservation of energy. Now first thing we need to understand the conservation of energy, that in our in our usual days the energy is always conserved. Like for example, if I'm having a ball in my hand, and if I just drop it, what will happen? It will go on the ground, and just before it getting on ground will it have some velocity. Think about it, from where this velocity is coming. It is coming because of the whatever the energy which was stored in form of the gravitation, now it is converted into the kinetic energy. Now what has happened is the one form of the energy is converted to the another form, but still the total energy is constant. The same thing happens here as well. According to the Lenz law, it is a fundamental thing of the universe that the total energy is conserved. So it means like from the loop, in a loop there is some electromotive force generated which is going to create a current and which is going to give us the power, right? So we are going to get the energy from the loop. If you are going to get the energy from the loop, then you must do some kind of work, right? So it means if there is a electromotive force which is generating the current in that, now this current which is generated, now let's relate this current to the previous chapter. So if this current is generated, then it will create a induced magnetic field. Now this induced magnetic field in the circuit will be in such a way that it will oppose whatever the cause is there for this generation of this, right? So in basic terms we can say that induced EMF will be in such a way that the magnetic field which is induced because of that, it will oppose the cause. So like for example, just a simple example we can understand here. Like here I have this magnet, and if I'm moving this magnet like this, then this magnet must be repelled, then only I will be doing some amount of work. Let's suppose if I bring this magnet this side and it is attracted, so what will happen? It is also getting the kinetic energy, and this is also getting some kind of electrical energy, which is not possible. It means if it is moving like this, then somehow the current will be created in such a way that which will generate a induced magnetic field, and the north of that magnetic field will be in this side and this north will be repelled. So hope you understood this part. Now many places will do like this, and then gradually we'll also understand by practice that okay, here in this loop the current is going to be like this, okay, and then the other place is the opposite of that. Sometimes there is also a shortcut like this, that this is a loop and this is a knot like this, so we'll bend it a little bit and we'll put the arrow. It means the current is going to go like this. Sometimes we'll put a south and this is south, so the current will be like this. Okay, so many places we do like this. Okay, so this is a shortcut to identify the current direction. Okay, now sometime what happens, instead of changing the flux, what we do is we move the whatever the conductor is. Okay, it can be a conductor as well, or it can be a loop as well. Okay, let's suppose if there is a conductor like this, so then if the conductor is moving like this, we can hypothetically consider a loop like this. Then this loop is, let's suppose this point is fixed and this is moving, then of course the flux is changing because the area is changing. Because if you look at the flux is b vector dot a vector. There are many ways we can change. We can change the magnetic field, we can change the area, or we can change the angle between the magnetic field in the area. And here what I am doing is I am changing the area by moving this. And if we calculate the EMF because of this, that comes out to be BLV. And now what is the direction of this EMF? We can apply the Fleming's right hand rule, where thumb will denote the motion of conductor and the index finger will denote the field line, and then the nearby finger will denote the induced current. You can just try to apply this on this. Okay, where induced current direction will give, many times instead of induced current we can just have the battery. So direction of the induced current is the kind of like you have the positive side there. So because here if you do the calculation, the induced current will be like this. Okay, so it means the upper side will be a positive terminal and the lower side will be behaving like a negative terminal of battery, if this is going to behave like a battery. Okay, now the another way of creating the EMF is with the help of the rotation. Okay, I was moving like this, now also I am moving little bit like that only, but I am rotating like this, still it is moving only, and there we get this EMF is b omega L square divided by 2. Now see, if I have a disk, then also like this will have the batteries, and these batteries are in parallel combination, so that's why the EMF is going to be same, b omega L square divided by 2. And in this sense of rotation with this magnetic field, this EMF of the battery will be like this. This outer side will be positive, inner side will be negative. This is important. Many places, like if we do a direction problem, then we might get the just opposite answers. We will be correct in the magnitude, but sometimes they also ask us the direction. So that's why the direction is very important to understand. Okay. Now, what if, like I was saying, that we have this flux. Flux is B vector dot A vector. Now let's suppose I have got some loop like this, hypothetical loop like this, or maybe a disk like this, and then I am varying the magnetic field. Now there will be some EMF, E is equals to minus of d phi by dt, and phi of course can be known as B vector dot A vector. I am not changing the area, so area is constant, and B is changing, so B will become dB by dt. Area will be, let's suppose I have a circle like this, so area will be pi r square. So I pi r square times of dB by dt, this will be the EMF created on that, right? Now EMF can be written down as E vector dot dl vector, and this is a closed loop, so that's why integration of that. So then you will say integration of E vector dot dl vector is equals to pi r square times of dB by dt, right? And now this dr, you can replace it with the 2 pi r, because you are taking a loop. So total integration E vector is something like this, and dl vector will become total, E is constant and 2 pi r, this dl will become 2 pi r. So from there, if you calculate the electric field, so electrical field becomes r by 2 dB by dt. Okay, all right. Now we were talking about the loop. Okay, let's suppose we have connected a battery in this loop. Okay, we have connected a battery in this loop. At t equals to 0, we have started the switch. As soon as we will start the switch, the current will try to increase. So if you look at the flux at any time t, the flux is going to be Li. Okay, L is just a constant here, some constant, or flux you can say is something pi r square. Okay, and times of B magnetic field. So flux is somehow, it will be dependent on the current. Then if you differentiate this, then you will get the, according to the Faraday's law, you will get the EMF, which is minus d phi by dt, and that will be minus of dl by minus of L di by dt. So from here, one thing I understand, that whenever I have a loop like this, and if I try to establish a current, if the initial current was 0, okay, and if I try to establish a current in a loop, initially there will be a resistance. Now if you look, this kind of resistance we have already faced in many other places as well. Like if I have a object on the ground, and if I try to move it with some velocity, initially I need to apply some force and then get it to a velocity v, then it can keep on moving if it is a smooth surface. And the same way, if there is a rigid body like this, and if I want to rotate with omega, then first I need to apply some torque, and then if I can set it in the omega, then it will continue to rotate with omega in the ideal conditions. This is because a body which is in rest will try to be in rest, and the same way it goes for the rotation as well. And same way, something similarly conceptually is happening in the current as well in a circuit. When you try to establish a current in a circuit, then there is a inertia, and you can name this inertia as electrical inertia. Now this inertia we are calling here in our syllabus this as the self-induction. What happens when you try to establish a current? So then there is a opposition, and this opposition is going to depend on the geometry of loop, and it is going to depend on the medium. And this is a formula, E equals to minus of L di by dt, and how it has come I have told you, right? Now this L, if you calculate for a solenoid, so then it comes out to be mu naught n square pi r square L. Okay, where mu naught is the whatever, if I am taking it as vacuum, so then that is the permittivity of permeability of vacuum, and n is the number of loop per unit length, and pi r square r is the radius, and L is the length. And if you divide this with the volume, of course the volume of the solenoid is pi r square L, so then if you get, then this will be the mu naught n square. So this is the induction per unit volume, mu naught n square, self induction per unit volume. Now what happens is, I was telling about you about this in about a loop. So when you try to establish a current in a loop, so then it will oppose. Now what about the inductors, or if for the multiple loops, so it will also oppose. And the same way I can say that EMF which will be generated in that will be equals to minus of L di by dt. So from here, this minus sign is also giving us the direction of the EMF. So like for example, if you are trying to increase the current in this inductor, so then this dl by dt is positive, so it means EMF will be negative. So if you move like this, EMF will be decreasing, so that's why this will be a positive terminal and this side will be a negative terminal. All right, what if I decreasing this, if I'm decreasing di by dt, so then this will be negative and overall it will be positive. So if I'm moving like this, then EMF must increase, so this will be negative and this will be positive. Now we can also get the energy stored in the inductor. With the help of this diagram, we can find out the current at t time, and we can find out the work done. With the help of that, we get the energy stored, that comes out to be half Li square. It is something like half Cv square. Parallel to that, okay, we get this formula of the energy stored in the solenoid, half Li square. And one more thing, just like there, in case of the electric field, we had this half epsilon naught E square. This was the energy stored per unit volume, half epsilon naught E square. And in case of the magnetic field, the energy stored per unit volume, if we calculate with the help of this formula, it will come out to be B square divided by 2 mu, where mu is the permeability of that medium. Now current in a RL circuit. Okay, so we have a inductor. Of course, in case of ideal inductor, there will be just the induction, but in case of the practical inductor, there will be induction plus also the resistance of that wire. So it will be practically a RL circuit, and RL circuit we can solve same like the RC circuit. So we can just form a differential equation, and then we can get to the I will be E divided by R, 1 minus E to the power minus of RL times of T, where we define this L divided by R to be time constant, right? Time constant means the point where the current becomes 63%. Okay, all right, so current will be increasing something like this. Okay, so in case of the parallel combination, we'll have the total inductance 1 by L equals 1 by L1 plus 1 by L2. We can do the calculations of this, and the series combination, in the series combination, total inductance will become L equals to L1 plus L2. Now let's come to the another point, which is the mutual inductance. What happens, like for example, I have this first loop, right, and I am providing some current in the first loop. Let's keep the another loop nearby. So if I am providing the current in this, then there will be some magnetic field. Now this magnetic field will be associated with this next one. Now this magnetic field is associated in this, so there is a flux associated with this. And now because this current is changing, so this flux will change. And if this flux is going to change, so then there will be a EMF generated in this. And like we had E equals to minus of L di by dt, here also we'll say E equals to minus of m di by dt, but E, let's suppose if I'm saying the E of this one, then the current, I will take the current of this one. Then this constant will be called as the mutual inductance. It means I'm changing the current in first one, and that is generating the EMF in the second one. Now in a perfect combination I have calculated, where these two loops are kept like this coaxially. So I have calculated the m, and m will be equals to root of L1 L2. If that is not a perfect coaxial, so then it will be lesser than L1 L2. And in case when you keep these two inductors like this coaxially to each other in series combination, and if you also consider the mutual inductance, then the total inductance of the circuit you are going to take is L1 L2 plus 2m. Why 2m? Because this will also have m and this will also have the m. One more thing, if you calculate the mutual inductance of the two because of 1, okay, this if you calculate, and if you calculate the mutual inductance of 1 because of the 2, both are going to be same. This follows the reversibility. So yeah, then next comes to the transformer. So we got this E is equals to minus of d phi by dt. So where phi flux is proportional to the number of the coils. So in the transformers, what we do is we have the primary coil, and in the primary coil will give some current, so there will be some flux. Now we will put a magnetic material here which will link this flux to the next one. Now this flux will change, and of course this flux will change, and now this flux is changing, so then this flux is changing, so this changing flux is creating the electric field here, or the EMF here, and that is creating the current in this. And then if we calculate the relation, so then this relation comes out to be, let's suppose EP is the EMF or the potential difference across the primary coil, and the ES is the potential difference across the secondary coil. That will be equals to number of loops in the primary coil and number of loops in the secondary coil. Now on that basis we can divide this transformer into the two categories. One is the step down and another are the step up. So for the step down I will have the less ES compared to the EP, right? So it means NS will be lesser than NP, and this reverse in the step up transformer. Now how do we calculate the current? Because see, in the ideal condition, whatever the power I will provide, that same power will be consumed on the secondary. Of course there will lot of other losses like the stresses losses, then there may be some flux is not able to link, so there is some flux going outside of the core material as well, so there will be some that kind of losses as well. So if we do not consider, and if we consider the ideal condition, in case of that you can say the power input in the primary circuit must be equals to power output in the secondary, and power can be written down as E, the potential difference times of current. So current in EMF in primary, current in the primary is equals to EMF in secondary times of the current in secondary. Now see here, the relation for the current will become just opposite, because the ratios of the IP divided by IS will be ES divided by EP, just opposite of that. Okay, now the last thing in this chapter is the AD current. Now let's suppose we have something, a disc like this, and now I am applying a magnetic field on that, and I am changing this magnetic field. Now if I am changing the magnetic field, then it will create the change in the magnetic flux over here. If there is change in magnetic flux, then there will be change in the there is a EMF which is created, and which EMF if it is created, and if we write down the EMF as integration of E vector dot dl vector, so then we can get the electrical field. Electrical field will equal minus of R by 2 dB by dt. And if you want to calculate the current, you can also calculate the current. Let's suppose if I go to the R radius loop, then I can find out the resistance of that R radius loop, I can find out the EMF of that R radius loop, and then I can apply V equals to IR, and I can get the current in this loop. Now one more thing about these, the electrical field which is generated is forming a closed loop, unlike our electrical field of this electrostatics. So here this electrical field becomes non-conservative. It is not conservative because it is forming a closed loop, and so that's why if we calculate the curl of that electrical field, so it is going to be non-zero. So that's why it is rotational field, and that is why it is non-conservative. So this is all about this chapter. I hope you must have understood all the concept. The purpose of this video is just to revise you the concepts and the formulas, and make a linkage of all these concepts with each other and the previous chapters and the coming chapters. Okay, so this is all about. There are the other videos available on the channel, and there are the conceptual videos and JEE mains and the JEE advanced videos. If you liked this video, you can just share it with your friends. Thank you very much.